Hello, students. We are checking out Math Connections in Module A. And Math Connections, I had question 2 and then 5, 6, and 7. So not a ton. Question 2 over here says, for all A, B, C, and D, explain why A, B, C, D as a number is equal to A plus B plus C plus D mod 9. Right? And then if we're in base 5, it will equal A plus B plus C plus D mod something. So we're trying to make a nice connection there between the number bases we've seen before and the division that we're encountering now. So A, B, C, D as a number, again, that is a base 10 representation. Doesn't have any other base there, so base 10. So think about what that means. That really means 1,000 times A plus 100 times B plus 10 times C plus 1 times D, right? Now it's beautiful. You're working in a mod 9. So anytime you see a number that's equivalent, you can replace it. Anytime. The same is true in base 10 if we're not working in mods. If you saw the number 28 and you wanted to replace it with 30 minus 2, you could do that anytime you want because they are equal. So what we're going to do now is we're just going to say, okay, what else could we do? Well, let's take a look at some numbers and see how close we can get. So we're thinking about base 10, but we're going mod 9. So here's a number 10. What is 10 equivalent to mod 9? 10 is equivalent to what? Mod 9. Okay, so 10 has the same remainder as what? And you say, well, wait a minute, in mod 9, I can just add or subtract 9. So I'll just take 9 away, and that's a 1. 100%. So when you come down, you could actually rewrite this as a number 1 because it is congruent. So you have 1C plus 1D. There we go. Now do the same thing for 100, right? How could I rewrite 100? And you could rewrite 100 as 91. You could rewrite it as 82. You could rewrite it as 73. So you have a lot of numbers you could write it as, but try to pick one that works really nicely. Mod 9. What's a good one to choose? So you're going to have a group of B's, and over here you're going to have a group of A's. If you needed to kind of break that up for yourself, you could say, well, remember 10 is equal to 9 plus 1. You are absolutely right. But in a mod 9 system, 9 acts like 0. So 0 plus 1 would just be 1. And that would be congruent mod 9. That's the idea. Okay, so we try to simplify things, and if we can simplify things, it makes it significantly easier. So that was 2. I think I gave you 5 through 7 as well. And so we have a few students who are like, hey, what's going on with this? So if you had a 5 clock, the one we did back earlier, if you scroll up, you can see it again. On the 5 clock, there is no 5. So the student says there can be no additive identity. So how are you going to respond to a student who says an additive identity is 0, right? So again, if you're thinking back, picture what is acting like 0. The true definition of an additive identity is that you pick any number, add it to something, and get back to the number you started with. The additive identity does not have to be 0. The additive identity of natural numbers is of whole numbers is 0. The identity of integers is 0. Of rational numbers is 0. But it doesn't say it has to be 0. It just has to be a number that I add and get back to what I started with. Okay. Let's see, what else do we have? Allie wants to know what elements of 5 have a multiplicative inverse. What do you tell her? Interesting. So if you watched a few of my other videos, there is a really nice connection between multiplicative inverses and the number that you're choosing here. It does relate back to other concepts we learned in Math 105, and hopefully you'll be able to spot those. And lastly, what do we have? Dan. Dan is trying to see how fractions like 1/4 might work in a 5-hour clock system. He said that he showed that 1 divided by 4 is greater than 3. But how is that possible? Okay, so in his mind, when he sees 1/4, he says that has to be less than 1 because 1/4 of it is less than 1. So how does that relate in this system where 1 divided by 4 might not be that, right? In this case, 1 divided by 4, if you want to check it, is actually 4. So how can, in his mind, 1/4 actually equal 4 as we go and take a look at this? So might be a good chance for you to talk with Dan about what does it mean to do division? What is the result of division, right? And how fractions, thinking of fractions, if I took that fraction in a sense and multiplied it by this number, would it still hold true? So if you wanted to think of 1/4 in the clock, right? And you multiplied by 4, would I still get back to 1? Right? Like, does it cancel kind of in the same type of way? Does the result actually hold true? So that's a good way to kind of approach Dan if you were needing a nudge. Otherwise, I think that about wraps it up. Let me make sure I answered all of these questions. Yep, none of the group work ones for this case. Yeah, I think that'll about do it. I had a cooperative learning one where I wanted to try one. I may try to do this one in class where I have people create a 3, 4, 6, and 11-hour clocks with the multiplication tables to kind of see the connections. Like, when can I do the division? When can I not do division? But we'll have to see. That might be time permitting. All right, that's it for now. Take care. Off you go.